Two identical spacecraft, launched just 16 days apart in 1977, both eventually crossed the exact same boundary, the edge of our entire solar system, and became the only two human-made objects to ever enter interstellar space. But when the first one made that crossing back in 2012, it did so essentially blind to the single most important measurement scientists actually needed. Its own plasma instrument had failed 32 years earlier, decades before it ever got anywhere near the boundary it's now famous for crossing. When the second spacecraft made that same crossing 6 years later, its equivalent instrument was still working perfectly, and what it measured directly contradicted, complicated, and ultimately rewrote what scientists thought they understood about the edge of our entire solar system. This is the real story of what Voyager 2 did that Voyager 1 physically could not. Why a single working instrument aboard a nearly 50-year-old spacecraft ended up producing 5 separate scientific papers in one of the most prestigious journals in astronomy, and why that specific gap in Voyager 1's own data has never actually been filled. If you want accurate space history explained properly, subscribe now, because this particular story doesn't get told nearly often enough. Let's start with the actual failure that set this whole story in motion, because it happened remarkably early in the mission, decades before anyone even knew it would eventually matter this much. Voyager 1's plasma science instrument, a device specifically designed to directly measure the temperature, density, and flow velocity of the charged particles surrounding the spacecraft, both inside our solar system's protective bubble and eventually beyond it, stopped functioning back in 1980. That failure happened before Voyager 1 had even reached Jupiter's orbit on its outbound journey, more than 3 decades before the spacecraft would eventually cross into interstellar space at all. For most of the mission, that failure didn't matter much because Voyager 1's other instruments, a magnetometer, a cosmic ray detector, and a plasma wave subsystem among them, continued providing valuable scientific data throughout its journey past Jupiter and Saturn and onward toward the edge of the solar system. But that early failure became a genuinely serious problem in August of 2012. The moment Voyager 1 crossed the heliopause, the outer boundary of the vast magnetic bubble our sun inflates around the entire solar system, and became the first human-made object in history to actually enter interstellar space. Scientists desperately wanted direct measurements of the plasma on both sides of that boundary at the exact moment of the crossing, precisely the kind of measurement Voyager 1's own plasma instrument had been specifically built to provide. Instead, researchers were forced to work around a 32-year-old gap in the spacecraft's capabilities, inferring what was happening from the instruments that did still work, the cosmic ray detector, the magnetometer, and the plasma wave subsystem, without ever being able to directly confirm the actual temperature, density, and flow characteristics of the plasma Voyager 1 was now sitting inside of. If a story built on real, verified NASA and JPL reporting instead of exaggeration is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Voyager 2 tells a completely different story, and the reason comes down to the two spacecraft's very different journeys through the outer solar system. Voyager 2 launched on August 20th, 1977, 16 days before Voyager 1, but was placed on a longer, more complex trajectory specifically designed to take advantage of a rare planetary alignment, allowing it to become the only spacecraft in history to fly past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune in a single mission. Voyager 1 took a faster, more direct route, visiting only Jupiter and Saturn before angling out of the plane of the solar system entirely, prioritizing a closer look at Saturn's moon Titan and a quicker path toward interstellar space over visiting Uranus and Neptune at all. It's worth understanding that this plasma instrument story isn't actually the only thing Voyager 2 accomplished that its twin never could, because its unique trajectory past all 4 giant planets produced its own separate list of firsts. Voyager 2 remains the only spacecraft in history to have visited Uranus, and during its January 1986 flyby, it discovered 10 previously unknown moons, 2 new rings, and measured a magnetic field so strangely offset from the planet's own rotation axis that it still challenges models of how planetary magnetic fields form in the first place. It also remains the only spacecraft ever to visit Neptune, and during its August 1989 flyby, the final planetary encounter of the entire Voyager program, it discovered 6 new moons, measured supersonic winds reaching 2,400 kilometers per hour, the fastest ever recorded anywhere in the solar system at the time, and captured detailed images of Neptune's largest moon Triton, revealing active nitrogen geysers and strong evidence that Triton was originally a captured Kuiper Belt object rather than a moon that formed alongside Neptune itself. Voyager 1, having taken its faster, more direct route toward interstellar space, simply never had the opportunity to visit either planet at all. That difference in trajectory meant Voyager 2 didn't cross its own heliopause until November 5th, 2018, roughly 6 years after Voyager 1 made the same crossing. But Voyager 2's plasma science instrument, unlike its twins, was still fully functional at that point, having survived the entire journey without failing. When Voyager 2 crossed the heliopause in 2018, it carried a working plasma sensor that Voyager 1 had lost before the end of the Cold War. And it produced a dataset researchers have since described as genuinely historic, the first direct measurement of plasma on both sides of the heliopause, taken simultaneously as a spacecraft physically crossed the boundary for the first time in human history. 5 separate scientific papers, all published simultaneously in the journal Nature Astronomy in November of 2019, described exactly what Voyager 2's instruments found at that crossing, and the results contradicted existing models in ways that genuinely surprised a research community that had already been working with Voyager 1's incomplete data for 6 full years by that point. If you found this as fascinating as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth including the actual numbers Voyager 2's plasma instrument measured, because the specific figures help illustrate just how significant a direct measurement turned out to be compared to indirect inference. The instrument found that interstellar plasma just beyond the heliopause carries a temperature somewhere in the range of 30,000 to 50,000 Kelvin, hot by ordinary standards, but dramatically cooler than the plasma sitting just inside the boundary, which registered at tens of millions of degrees. That direct measurement of interstellar plasma temperature, something Voyager 1 was physically incapable of providing, gave scientists a real, measured baseline figure they had previously only been able to estimate from theoretical modeling. And according to researchers analyzing the result, that original theoretical estimate had actually been off by roughly a factor of 2. The plasma density measurements told a similarly important story, confirming that interstellar space beyond the heliopause is considerably denser than the solar wind found just inside the boundary, by a factor exceeding 40, giving both Voyager spacecraft their first genuine stereo measurement of interstellar plasma density once Voyager 2's numbers could be combined with Voyager 1's more limited indirect estimates. The first major surprise involved the actual thickness of the boundary itself. Scientists had expected the heliopause to be a relatively thin, sharp transition, a fairly narrow zone where the hot, fast solar wind met the colder, denser interstellar plasma, and the two environments blended together before cleanly separating. What Voyager 2 actually found was a considerably more complex picture, a distinct transition layer, roughly 100 million miles wide, sitting just outside the heliopause itself, in what was supposed to be interstellar space where the interstellar plasma was expected to begin immediately. Instead, Voyager 2 detected tendrils of interstellar material pushing inward through the boundary, extending more than 100 million miles into territory that existing models had assumed belonged entirely to the solar wind. The second major surprise involved something researchers hadn't even fully expected to be able to test directly: the relationship between the Sun's own activity cycle and the actual physical size of the heliosphere. Voyager 1 crossed the heliopause in 2012, near a period of relatively high solar activity, at a distance of about 121.6 astronomical units from the Sun. Voyager 2 crossed 6 years later, during a period of comparatively low solar activity, at a distance of about 119 astronomical units. Existing models predicted the heliosphere's size should expand and contract meaningfully with the Sun's roughly 11-year activity cycle, meaning the two crossings, happening at different points in that cycle, should have occurred at noticeably different distances from the Sun. Instead, both crossings happened at nearly the same distance. Stamatios Krimikis, principal investigator for one of Voyager's instruments at the Johns Hopkins Applied Physics Laboratory, addressed that specific discrepancy directly, stating plainly that scientists simply don't understand why that is, a genuinely rare and notable admission from a senior researcher with decades of first-hand experience working with this exact data. The third finding, and the one Voyager project scientist Ed Stone at Caltech specifically called the most remarkable of the entire dataset, involved the boundary's basic structure. The heliopause, it turned out, isn't a clean, sealed wall separating our solar system from everything beyond it. It leaks, genuinely and measurably, in both directions. Voyager 1, on its own approach back in 2012, had already detected what appeared to be tendrils of interstellar particles pushing inward through the boundary from outside. Voyager 2, approaching from an entirely different direction 6 years later, detected something complementary, a trickle of low-energy solar particles leaking outward into interstellar space before the spacecraft had even technically crossed the boundary itself. Two spacecraft, approaching from different directions at different points in the solar cycle, both independently confirmed the same underlying conclusion, that particles cross this boundary regularly in both directions, a genuine two-way exchange rather than a sealed one-directional edge. Stone summarized the broader significance of these findings in a way that's worth repeating directly, because the specific wording matters. He described what the Voyager probes were showing scientists as how the Sun interacts with the material, filling most of the space between stars and the Milky Way galaxy, deliberately choosing that phrase over any language implying a clean separation between our solar system and everything beyond it. Not where the sun's influence ends and interstellar space begins, but how the two regions continuously interact with each other, an ongoing, messy, dynamic relationship rather than a simple boundary line on a diagram. These findings also fed directly into a much broader, still unresolved question about the actual shape of our entire heliosphere, something scientists can observe directly from outside the way you might photograph the shape of a soap bubble from across a room. Some models predict the heliosphere has a long, comet-like tail stretching away from the sun's direction of motion through the galaxy, while others suggest a more rounded, or even distinctly lemon-shaped structure. Voyager 1 and Voyager 2 sampled two different points along that structure's outer edge, one closer to what researchers believe is the nose of the heliosphere, the other closer to its flank, and their combined data, especially Voyager 2's direct plasma measurements, remains one of the primary tools scientists have for actually testing which of those competing models comes closest to reality. Every additional year, either spacecraft continues operating adds more data to that picture, which is a large part of why engineers have gone to such lengths, including this year's experimental Big Bang power-saving procedure, specifically to keep at least one plasma-related instrument running on each spacecraft for as long as physically possible. It's worth being direct about why none of this could have come from Voyager 1 alone, no matter how carefully scientists analyzed its other instruments. Every one of these three major findings, the unexpectedly thick transition layer, the puzzling consistency in heliopause distance across different points in the solar cycle, and the direct confirmation of particles leaking in both directions, depended specifically on Voyager 2's still-functioning plasma instrument providing a direct measurement of temperature, density, and flow velocity that Voyager 1 simply had no way to gather after 1980. Voyager 1's other instruments provided valuable complementary evidence, but the plasma measurements that actually anchored these 5 Nature Astronomy papers came entirely from Voyager 2, filling a scientific gap that had existed in Voyager mission data for 38 years by the time Voyager 2 finally closed it. That gap in Voyager 1's own capabilities has never actually been filled, and it never will be. There's no way to repair or replace a failed instrument on a spacecraft currently sitting more than 15 billion miles from Earth, and there's no third Voyager mission planned or funded to go back and gather the specific measurement Voyager 1 lost back in 1980. Whatever Voyager 2 managed to capture at its own heliopause crossing in 2018 represents, and will likely remain, the only direct plasma measurement humanity has ever gathered at the exact moment either spacecraft crossed into interstellar space, a genuinely unique data set that exists because one specific instrument on one specific spacecraft happened to keep working just long enough to matter. Both spacecraft remain active today, still transmitting data from interstellar space, though both are now dealing with a separate, unrelated challenge entirely: the slow, mathematically certain decline of their onboard power supplies as the plutonium fueling their radioisotope thermoelectric generators continues to decay. As of the middle of 2026, engineers at NASA's Jet Propulsion Laboratory have been forced to shut down several of each spacecraft's remaining instruments to conserve power, including Voyager 1's low-energy charged particles experiment this past April, following an unexpected power drop in February that came dangerously close to triggering an automatic safety shutdown. NASA has been testing an experimental power-saving procedure nicknamed the Big Bang, first on Voyager 2 during May and June of this year, with a similar attempt planned for Voyager 1 no earlier than July, specifically in hopes of freeing up enough power to keep at least one science instrument running on each spacecraft into the 2030s. As of this recording, the final outcome of those tests hasn't been publicly confirmed, and whatever the result turns out to be, it won't change the fact that Voyager 2's plasma instrument already did something back in 2018 that its own twin was never able to do again. So what does all of this actually add up to? Voyager 1. Well, 1 made history in 2012 as the first human-made object to enter interstellar space, but it did so without the ability to directly measure the plasma responsible for defining that exact transition, because its own equivalent instrument had failed 3 decades earlier. Voyager 2 crossed that same boundary 6 years later with its plasma instrument still fully intact, and the resulting measurements, published across 5 separate papers in Nature Astronomy in 2019, revealed a heliopause considerably thicker, considerably leakier, and considerably more puzzling in its relationship to the Sun's own activity cycle than any existing model had predicted. There's a quieter lesson buried in this specific story worth carrying away, one that goes beyond the plasma physics itself. 2 identical spacecraft, built from the same designs, launched weeks apart, ended up telling scientists 2 genuinely different versions of the same historic milestone, simply because one instrument on one of them happened to keep working a little longer than its twin. Nobody planned for that specific outcome back in 1977. It's simply what happened, and it turned out to matter more than almost anyone could have predicted at the time. filling in a scientific gap that no other spacecraft, before or since, has ever had the opportunity to close. If stories like this, real space history explained accurately rather than compressed into an oversimplified headline, are what you come here for, subscribe to this channel and turn on notifications, because there's a lot more of the real Voyager story still worth telling correctly. Thanks for watching, and I'll see you in the next one.